All right, this topic is on hybrid orbitals, and this involves the mixing of atomic orbitals to make these hybrid orbitals. We'll look at the details here. Usually we start the discussion with carbon. So many different molecules are made from carbon. And if you remember, carbon has 6 electrons and 6 protons, the electron configuration, 1s2, 2s2, 2p2. So we're talking about the valence shell electrons, and if you put them in the orbital diagram, you're going to have 2s2. Those electrons are going to be paired here, and then paired, and then you have 2p2. Remember Hund's rule, these two are going to be unpaired. Above you have hydrogen. It's a 1s orbital, 1s electron, which is going to bond with carbon. So carbon has 4 valence electrons, and then this is going to be the correct structure that we talked about in the last video. CH4 is tetrahedral, and it's 4 groups of electrons. Bond angles are 109.5, and those bond angles, every single bond angle is the same. Remember, these hydrogens fit into the corners of the tetrahedral pyramid. All right, now, if you use this electron configuration here, the unhybridized carbon configuration, this is the model here. So you have the carbon, and then you have one p orbital, so this one. You got the second p orbital, which is this one. And then what's not shown is that, well, I guess the up and down right here in the center, that indicates spherical s orbital with 2 electrons. All right, so then you can have 1 hydrogen per p electron, and so you would expect a bond here and here, and you can just see that this can the orbital diagram does not match this structure. So, in the next slide, here we have, again, the tetrahedral geometry from methane. And then if you have, this is the diagram that I just showed you on the last slide. This is the unhybridized carbon, excuse me, carbon electrons. And then the very last part of it is the new information. And the idea here is that you take these 1, 2, 3, 4 electrons, you mix them together to form these 1, 2, 3, 4, and they're called hybridized. The atom is hybridized, and they have these sp3 orbitals. Okay, so with the sp3 hybridization, it's completely different. So each one of the electrons is the same. This is an This is an sp3, this is an sp3, this is an sp3, and this is an sp3. And then it's just 1 electron in each one of these hybrid orbitals, and then the hydrogen contributes 1 electron, and then you have the octet. All right, so that's what we're going to talk about in the next slide, how you go from here to here. All right, so the analogy is that you have 4 cans of paint, and you could say you have a blue can of paint, a red, and 3 cans of red paint. All right, you mix them all together. You're still going to have 4 cans of paint, but they're going to be purple. So red and blue is purple, and that's the whole idea. And you can do that for electrons because they behave like waves. These, in fact, are standing waves. In 3 dimension, there's the node right there. And so waves can add together, that whole idea of superposition of waves. So you can add and subtract these wave patterns. And then what you get is 4 sp3 hybrids. And notice that it's got a little lobe and then a big lobe. So basically what you're doing is saying an S plus a P. You superimpose those two waves, and you're going to get 2. This would be for an sp hybrid, not an sp3, but just to give you the idea here. Also, the waves, like a sine wave, for example, it has like positive and negative characteristics. Positive above the line, negative below. Orbitals are like that too. So an s orbital has positive all the way around, and it's not charged. This is just about the phase of the wave. The p orbital has a positive and a negative phase relationship, and the node kind of defines the change in the phase. And so here, when you add them together, you're going to get a small negative part and a large positive part. So this, you got negative here and positive here. And then you can also subtract them. So you take 2 orbitals, you can add and subtract them and basically add them up and get the initial wave configuration. So this one is negative and positive as well. So if you mix an S and a P, you get 2, these are sp hybrids. And in the case of the sp3, you get 4 of them. But no matter what, no matter what kind of hybrid orbitals they all look the same. So there's a small part and then a big part like that. So each hybrid orbital looks the same. It doesn't matter if sp, sp2, doesn't matter what kind. Excuse me. So when you superimpose them, all 4 of them, then you leave out the little lobes, the small ones. It's just too much to put them in and try and overlap them, and it just looks very confusing. So you're just taking the big part and putting 4 of them together, and easily they fill into the corners of that tetrahedral pyramid. All right, so there's that. And then the other part of it is that once you have your hybridized orbitals, then hydrogen, so there's 1 electron for each one of the sp3 hybrids, and then there's 1 electron from each of the 4 hydrogens, so you get up, down like that for each bond. So this then becomes a covalent bond when you have this end-on interaction between the hybrid orbital and the hydrogen atom, excuse me. All right, so that is a lot in one slide. And then on the next slide is kind of a summary before we go forward. And the summary is that linear molecules that have 180-degree angles. Remember, a linear molecule has 2 bonds, and then they're 180 degrees from each other. They have sp hybrid orbitals. If it's trigonal, remember the bond angle is 120 degrees. Those molecules have sp2 hybrid orbitals. Tetrahedral, 109.5 degrees. And then trigonal pyramidal, or trigonal bipyramid, I think it should be. Bipyramidal molecules. They have d orbitals get involved in the hybridization. So those hybrids are dsp3, and those are 120 degrees if you remember, and 90 degrees and 180 degrees. And finally with octahedral, those molecules are 90 degrees. So the octahedral molecules have D2sp3. So I'm going to show you examples for all of them. All right, so then we'll start with beryllium hydride and just kind of go down this list, and you'll get a good idea of what this is. The next example was BH3. And if you remember the Lewis structure, right angles for this one. Boron has 3 electrons. So boron 1s2, 2s2, 2p1. So you got 3 electrons in the valence shell. And if you write out, well, back up. If you let these bonds be as far apart as possible, then you're going to get the planar triangular geometry with 120 degrees. So again, you can look in the table, you can memorize it, but with 3 bonds, 120 degrees, you're going to need 3, and this time we're going to mix an S and 2 P's together to make sp2 hybrids. So the sp2 hybrid is associated with that planar triangular, that 120 degree geometry. All right, so let's have a look at that. So just for the valence part of the electron configuration, like this. The next step is to hybridize. So we know what we want. We know that we want sp2 hybrids. So we're going to take one of these from 2s, put it into 2p, and then I like to rewrite it. Like this. Then again, we know that we're going to mix them together in S and 2 P's. So the next step here is to have 1, 2, 3. They all have the exact same energy. The S and 2 of the P's together make 3 sp2 hybrids. 1, 2, 3. And then the P is left over here, and it's empty. Now, you might ask, I usually get this question, why is it that we had n equals 2 here and then it was dropped here? You can put in the 2 if you want to do that. I tend not to do that. But if you felt better about it, you could put a 2 there. That'd be fine. All right, so then the drawing is going to be, you have boron in the middle. You have the first sp2 hybrid, the second sp2 hybrid, and the third sp2 hybrid oriented at 120 degrees from each other. And then bonding with hydrogen, make sigma bonds. Label each one as a sigma bond, and that's going to be boron hydride. Looks a little funny though, right? But that would be the correct answer for the hybridization. It gives the correct geometry. All right, so the next one is going to be methane, and we've already done methane, so CH4 is next on the list. And this gives 4 sp3 hybrids, 109.5 degrees. The next one on the list is NH3, okay? And so if you look at the Lewis structure for NH3, it's going to look like this. I like to put circles around my lone pairs. And then that's right angle geometry. Now, the key here is that you have to include the lone pair into the count. So the question is, how many groups of electrons are there here? And the answer is there are 4. So 4 groups of electrons, and therefore the hybridization is going to be sp3, like methane. And let me write that a little differently. You need 4, sp3 hybrids. Okay, so that should be the logic up to that point. Now let's look at the orbital diagram for, so you have nitrogen, which is going to be 5 electrons in the valence shell, 7 total, 1s2, 2s2, 2p3. So there's 5 electrons in the valence shell. You have 2s, 2p, 1, 2, 3, 4, 5. And in this case, you don't really have to promote I mean, if you mixed them together, you would get the same result, but consistent with the idea that you take one of the S's and then 3 of the P's and combine them. I like to write this step out anyway. Okay, so the next part would be like that. And then we're going to mix them together, sp3 hybrids. So it'll be 1, 2, 3, 4, sp3. There's 5 electrons, 1, 2, 3, 4, 5, like that. So then the next step is to draw it as a tetrahedron, where you have nitrogen in the middle. And as you know, I like to put the lone pair in the plane. Whoops, I can't do that. Yeah, when you're drawing out those hybrids, you can't make them look like 2 are in the plane, one's coming forward, one's going back. So don't even try to do that. But they're all sp3, even the one with the lone pair. And then the next step is to come in with the hydrogens. And I guess I could do that S, or you call them H if you want to do that. Then you've got the sigma, there's 3 sigma bonds there. And I guess that's basically it. Yeah, that would be the answer to that one. All right, the next one is water. And the Lewis structure will look like this. So you say there's 4 groups of electrons. Therefore, I need 4 sp3 hybrids. And we got to mix an S and 3 P's. And so we know where we're headed on this one. Oxygen is 1s2, 2s2, 2p4, right? That's the valence shell. So now you have 2s, 2p, 1, 2, 3, 4, 5, 6, like that. All right, again, with these you could just mix them, but just to be kind of consistent with the pattern, I will promote. And by the way, it takes energy to promote an electron to a higher orbital, but then once the hybridization takes place, then the energy is regained and then some more as well. So in the end, the hybrid orbitals have lower energy than the unhybridized ones, and that's the motivation for it. Okay, so then we're going to mix them together. 1, 2, 3, 4, sp3 hybrids. There's 6 electrons. 1, 2, 3, 4, 5, and 6. Whoops, that one. Okay, and then now you're going to draw it as a tetrahedron. And the only way you can really do that is to label sp3, 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 and then put the hydrogens in, 1, 2, label them sigma, and that would be the answer for water. Looks kind of weird, doesn't it? All right, and so let me list here. Where's my list? Okay, so the next one is PF5. So PF5, if you remember, phosphorus is right under nitrogen in the periodic table. And let me look at the number of electrons that hydrogen has. I can't see very well, 15. So it's got 15 electrons, 1s2, 2s2, 2p6, 3s2, 3p3. these are the valence electrons. So remember, we had 1, 2, 3, 4, 5, where phosphorus is gonna not obey the octet rule. Then there's 5 fluorines. Each one has 1 electron that makes the bond. And then there's all these lone pair electrons as well. 6 for each fluorine. Okay, so for this one, the hybridization is different, and there is a 3D0 as part of the configuration. So 3D would be there, and electrons can be promoted into that. They're not going to be promoted into the 4s2. They're going to go into 3D. And so if you have 5 groups of electrons around the central atom, then you're going to need 5 hybrid orbitals, an S, 3 P's, and a D. Okay, so you can think of this as 1 S, 3 P's, and 1 D, but we don't write down the ones. Okay, so this is different, and we can start with the orbital diagram. 3s, 3p. There's none in there right now in the 3D. So you got 1, 2, 1, 2, 3. All right, you know what you got to do here. You've thought it through. You got to put 1 electron into the D, because that's going to be part of the hybridization. So for this promotion step, include it. And you have S, P, and D. 1, 2, 3, 4, 5. So you got all single bonds, so it's going to be 1 electron in each one of those. And now you're going to hybridize. You're going to mix them together. So it's 1, 2, 3, 4, 5. S, 1s, 3 p's, and 1 d mixed together. So 5 atomic orbitals make 5 hybrid orbitals. And then 1, 2, 3, 4 d's up here, nothing going on there. All of the electrons are part of this hybridization. Okay, so that's how you do it. Then you're going to draw it, what was it? Phosphorus, right? So phosphorus. Okay, so you're going to draw that triangle. 5 groups of electrons. It's going to be trigonal bipyramidal. So you're going to have your first 3 hybrids will be in the plane of the triangle. Each one of these is sp3d. And then you're going to have one above the plane and one below the plane of the triangle. And they're all going to be sp3d. Okay, then it was bonded to fluorine. And before we go on, you have 120 degree. This is 120 here. And then there's, 90 degrees to the, from the upper and lower ones to the plane of the triangle, and 180 and whatnot. Okay, so then the next part is to look at the sigma bonds to fluorine. And if you go back and look at fluorine, you have to do it. You have to go through it. But fluorine has, when bonded, it's got 4 groups of electrons. So then it's going to be tetrahedral geometry. So this is going to be sp3, 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 and then these are lone pairs. Okay, it gets complicated, right? So for each one of these, it's the same. sp3. And now if you actually read about this in your book, it says that fluorine is kind of an exception. It's got quite a bit of P character and not so much hybridization. It's got some, but not a lot, I guess. And so, yeah, it's a little complicated, but this is the way it would work if it were not complicated with the P character. You label each one. Then what other color am I missing here? None of them. I'll use red. You're going to label sigma, 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 and sigma. There's 5 sigma bonds. This gets very complicated, but you can do it. Students say sometimes it looks like a big flower. Okay, so that's PF5. The next one is SF4. And so for this one, SF4, you have, let's see, are there 4 groups of electrons? You don't really know this until you look at sulfur, which is just underneath oxygen in the periodic table. And it's going to be 1s2, 2s2, 2p6, 3s2, 3p4. Okay, so there's 6 electrons in the valence shell. 1, 2, 3, 4, 5, 6. Put your fluorine bonds as close together as possible. And then there's this lone pair. So there's 5 groups of electrons. Therefore, you're going to need 5 sp3d hybrids. And one of them will be a lone pair. Let's see how that works out. You start with sulfur, 3s, 3p, 3d. I'm scrunching them together to make a little bit more room. So you have 1, 2, 3, 4, 5, 6, and the D's are not filled, but you know that you're going to include the D, so take one of your S's and pop it up there, excuse me, into that 3D section. Then you're going to have 3S, 3P, 3D, 1, 2, 3, 4, 5, 6, like that. Then mix them together, 1, 2, 3, 4, 5, with 1, 2, 3, 4, 3Ds left empty. And this is, some people write DSP3, some people write SP3D, same thing. Now you got 6 electrons, so it's 1, 2, 3, that one flopped there. 1, 2, 3, 4, 5, 6, like that. So there's your lone pair. Then you can draw it. So you have sulfur, 1, 2, 3, no. You have sulfur, and there's 5 groups of electrons, and if you remember, the lone pair goes into that plane of the triangle. So here's the triangle, the lone pair is in the plane. Then you have 1 above and 1 below. Each one is DSP3, DSP3. All All right, and then you have fluorines bonded to 4 of them. 1, 2, 3, 4. 1, 2, 3, 4. I don't know if you can hear my neighbors playing. Got 4 kids over there. Okay, and then you've got sigma bonds. 4 sigma bonds. And then you want to label the F orbitals as sp3. And then these are lone pairs. Okay, so 3 sets of lone pairs, and then 1 sigma bond. So you want to do that for each one. Label each one sp3, and you can continue to fill that out. All right, then 2 more to go. SF6 is the next one. SF6, if you do your Lewis diagram, there's 6 groups of electrons. I'm going to go faster here. So 6, you're going to need 6 hybrid orbitals, and it's going to be 6 sp3d2 hybrids. And I also spelled that wrong, but I also didn't draw it, right? So your Vesper structure, you probably I've been neglecting that, but you want to do that. Put in the lone pairs. I'll skip that for now. Okay, so you know what the geometry is. You know how many hybrids you need. You know that it's 90 degrees. And the next step is to look at hybridization of sulfur. So you're going to have 3s, 3p, 3d, and you have 1, 2, 3, 4, 5, 6. Then you are going to promote one of these here. And since you need 2 Ds, the second one will go over there. So the hybridization will be, not the hybridization, just the promotion. Gonna have 1, 2, 3, 4, 5, 6. And then you're going to mix them all together. 1, 2, 3, 4, 5, 6. sp3d hybrid or d2 hybrid orbitals. 1, 2, 3, 4, 5, 6. So that's the hybridization. The next step is to draw the square. Then put your hybrids there, one above, one below, and then they're going to be bonded to, I think it's fluorines again, yeah, fluorines, 3, 4. You can do a better job than I can here. Bond angles are 90 degrees, and there's 6 sigma bonds here. And you can label these sp3s, and these are going to be sp3d2, all 6 of them. And you can go ahead and fill all that in. And then also we have right, it's going to have these lone pair electrons. So you can go ahead and fill in the rest of that. Okay, one more and then we are done with this. So this one is SF5 minus. So this is a good example because it shows what to do with the extra electron. So you have sulfur with 1, 2, 3, 4, 5, 6 around the central atom. The negative charge is the 7th electron around sulfur. Then you're going to make 1, 2, 3, 4, 5 bonds to fluorine. And a lone pair, so there's 6 groups of electrons. Therefore, you're going to need 6, in this case, sp3d2 hybrids. And you would draw the VSEPR structure. Normally we put the lone pair below, if you remember. Okay, so we got all of that, and now quickly put it all together here just to show what to do with that negative. So you have S, P, D, and there are 7 electrons, 1, 2, 3, 4, 5, 6, 7. We know we're making 6 hybrids, so we're going to promote 1 from here and 1 from here into the empty d orbitals. Then draw that promotion scheme. So you're going to have 1, 2, 3, 4, 5, 6, 7. So you've included the negative charge into this count for the hybridization of sulfur. Okay, and so there's going to be a lone pair, and next we're going to mix them together. So it'll be 1, 2, 3, 4, 5, 6 sp3d2 hybrids with 1, 2, 3, 4, 5, 6, 7. So there's your lone pair. It's kind of fascinating to see how that all comes together. And you got sulfur. These are the hybrid orbitals. And then you got 1 above and 1 below. Whoops. 1 below. And the one below has the lone pair. The rest of them are bond. You could put hydrogens here, that would have been fine. But they all have fluorine, so. All right, so then you have 5 sigma bonds. 1, 2, 3, 4, 5. These all have the lone pairs. The hybridization is sp3. And the hybridization here is sp3d2 for each one of the 6. All right, I'll let you fill in the rest of it, and I'll leave it at that. I think I got one more. BeH2. So back to our Lewis diagram, you always start with that. And beryllium is one of those exceptions, if you remember. The configuration for beryllium with 4 electrons is 1s2, 2s2. So when n equals 2, this is the valence electrons. There are 2 electrons in the valence shell. So here they are, 1 and 2, and then each hydrogen contributes 1. So for your Lewis structure will be like this, and not necessarily linear. You could have right angles on the Lewis structure, it wouldn't matter. But then the VSEPR structure, if you make them as far apart as possible, then the VSEPR structure will be linear. And the bond angle is 180 degrees. So if you go back to the slide before, or actually the table in the last set of slides, it was the last slide, in Chapter 11, Part 1 video and slides where you can actually see the connections between the bond angles, the shapes, the hybridization, and how many hybrids you need and so on. So it's worth it to look at that. Anyway, so here you've got, you're just doing the valence shell here, 2s like this, and you have 2 p's are empty. So it's possible to populate those orbitals. If you give an s a little bit of energy, it can become a p orbital. And so that is called the promotion step. And your book doesn't do it, but I like to do it. I like to show how to promote. So what we're doing here is taking one of these electrons and putting them into the P. So then it's going to be one in the S and one in the P. Okay, you got 2 cans of paint at this point. One is red, the other one's blue. Mix them together. You're going to get 2 cans of paint. They're going to have the same color. Or in this case, you're going to mix the orbitals together. You're going to have 1 S and 1 P. Now, if I put a 1 on top here as a superscript, you probably understand better. I'm mixing 1 S and 1 P, but we tend to leave that out. Whoops. Okay, so 1 S and 1 P mixed together to form the SP hybrids. The other P orbitals would be available if we wanted to excite into them, but we're not going to. They're empty, so you can write them in or leave them out, depending on what you want to do. So then for beryllium, you have the first SP hybrid, the second SP hybrid, okay, and then you're going to mix, each one has 1 electron, and then you're going to come in with the hydrogen atoms. Now, hydrogen atoms are s orbitals. You can write s's there, or you can write H for hydrogen. Either way is fine. So now you're looking at covalent bonds, and if the orientation is such that the s orbital comes, like, it's called a end-on interaction. So, you know, the end of this is interacting with the end of that, and when they overlap, that's going to be the covalent bond. So that is referred to as a sigma bond. There's 1 sigma and the second sigma. This is a sigma covalent bond. And we use the symbol sigma. If you write it out, it's Greek letter, it's Greek letter sigma, and if you write it out, you just write out sigma there. And so that is the type of bonding. Okay, and I think we're good on that one. Oh yeah, and then the bond angle here is 180 between this one and that one. All right, so then right here, oh, okay. Guess I got mixed up a little bit. And then this one, this is just a picture of ammonia, and this is the hybridized system. And this is the lone pair. Remember, the lone pair is not bonded to hydrogen, and it doesn't show it here, but it's actually a little bit bigger, and it tends to push the electron, the hybridized orbitals that are bonded away from it. And so that's why the bond angle here becomes, it goes from 109.5 to 107. All right, and then there's one more, there's part 3 coming up for this chapter, and that's going to be on multiple bonding, double and triple bonds.